And they're just remarks. I'm sure all of you have been exposed to Cantor's theorem about infinitely many cardinalities, just to say very quickly, by a raise of hands, am I wrong? Who hasn't seen Cantor's theorem over his life? One. Okay, I hope this will be enough to appreciate the depth of that fairly simple theorem. In fact, let me start, if I manage, by pointing out that the theorem introduces an incredible proof method that has been repeatedly used later in important works. And there has been analysis of the method itself, and I found at least these references. I'm going to base my talk essentially on the first reference up there, and which was a paper by Bill Lovier, a very early paper by Bill Lovier, where he introduced the categorical point of view of the what is called now the carry-hour correspondence. So, and the fact that the lambda calculus, the type lambda calculus, presents itself canonically as a Cartesian closed category, and presenting several examples of such kind of categories, and in particular analyzing the proof of Cantor in that language and proving a certain result which we'll get to. The three other papers, well, one is a book. The first two refer heavily to the original paper by Lovier. The third one, for what I've been able to read, doesn't, although he's probably aware of the existence. The theorem. That's how I learned it. I was introduced to the two sets of the natural numbers and the real numbers a long time ago in my life, and I was told that it was impossible to count one using the other. In technical terms, there is no bijection between the natural numbers and the real numbers. And now I'll present to you the standard proof, which is used in essentially any first-year course in discrete mathematics, at least from the country where I come from, which is Italy. And well, you tell me if here the situation is different, or if you know that in other places it's different. So I have to prove that there is no bijection. Let's assume there is one and aim for a contradiction. If there is a bijection,
I don't need this.
Sorry?
I don't need to suppose that there is one infinite contradiction for me. It's not a real necessary.
I know. It was just a matter of speed. Yeah, you're absolutely right. It's a negative statement, so I just prove it. But I was doing it. You're absolutely right.
But you're doing what everyone does.
Yes.
Yeah, exactly. This is what
Everyone.
Let me go through it because I'm careful to see. I'm happy to see that you're very careful. Please keep your attention high at the moment. So, since I've assumed there is a bijection, I can list all the values of the bijection. It's a bijection from the natural numbers into the open interval of real numbers from 0 to 1. So 0 does not appear there, 1 doesn't appear there. There are all the numbers that are 0 point and then digits, not the sequence of digits which is constantly 0, just that. Well, maybe a few others. And suppose it's the one you see up there in the picture, take the diagonal. The diagonal is the diagonal that goes infinitely through the infinite matrix, and copy it. It's 0 dot, and then it is, if I copied it right, 7 0 5 9 1 6 0, and so on. Whatever remains on the diagonal. But after considering this number, which is probably a real number between 0 and 1, change all the digits. So, but for the first one, which remains 0 point. So instead of 7, say you write 8, instead of 0, write 1, instead of 5, write something else 4, and so on. Instead of 0, write something 2. I've written 1 before, but never mind, write 2 now.
You are assuming the final choice here. You should have an algorithm for changing it.
My God, you are paying attention. Thank you. I like that. The argument is not over. There may be mistakes in it, but the argument gets finished by the fact that by changing each of the diagonal entries in the number I've just written, the number B cannot appear in the first line, cannot appear in the second line, cannot appear in the third line, because it fails on the intersection with the diagonal. Yes, there are a few mistakes. There is one mistake, and I'm sorry to find in elementary textbooks that, yes, there is an implicit invocation of the axiom of choice in performing the construction of the number failing to be on the diagonal, failing the diagonal, if I may say. And there is also another thing, which if I want to make sure that I write the decimal expansion of a number between 0 and 1, I have to make sure that my choice is not 9999 from a certain point onwards.
But that's usually assumed. That's usually mentioned in the proofs.
That sometimes happen. I'm afraid I've seen cases where it doesn't happen.
Unfortunately, it's not in many expositions. They're wrong.
But there is actually, so you're familiar with this kind of proof.
Mhm.
And then the thing that I discovered is that this is not Cantor's proof, because what Cantor wanted to prove was something completely different in the first version of the theorem. He wanted to prove that there are many transcendental numbers. Transcendental real numbers are those real numbers which are not algebraic, which are not solutions of integer equations. And the proof goes exactly by cardinality. It proves that the algebraic numbers are countable, are in bijection with the natural numbers, and I spare you that proof is just there are finitely many that are solution of each equation. You solve the equations which are countable, and you get a countable set. But it proves that any open interval cannot be counted, and the way he does it is by a completely analytic proof. And that was my first surprise, because I've always known that the argument was the other. So the way he does it in the 1887 paper is consider a sequence of real numbers, and it's going to be, if I want to check whether the real numbers are countable, I have to consider sequences like any analyst would do, and consider any open interval AB. And then the case, can you see? Oh, yes. And then the cases, there are two cases. I can avoid cases, but let me do it with cases. Either in the interval, in the open interval AB, there is no value of the sequence, and I'm done. That interval is not covered by the sequence of real numbers, or there is a first one. Take it and consider now the interval which has that extreme point and the other one. Actually, it's on this side for you. And then look whether there is another element of the sequence in it, and take the first one that it's inside and restrict the open interval. And then do it again and restrict the open interval. You start getting a chain of inclusions of open intervals. It may stop there in the sense that the interval I've picked now doesn't contain any value of the sequence, and then we are done, the original interval AB is not covered by the sequence of.
One thing that I don't understand
Yes.
in our position. Here it seems that there is two orders that coincide one with the other. So the first one is alpha 7, the second one is alpha 12. And you suppose the alpha 2, the velocity is the first in alpha 7,
Yes,
alpha
yes,
12.
yes,
Okay,
yes,
okay.
yes, it goes
Okay.
flip-flop. And otherwise, you get a chain of open intervals, and there is at least an accumulation point which separates all the opens.
Naive question, perhaps. It does really mean that there are no other numbers, real numbers are not.
There are no,
There are other numbers that are not transcendental, right?
yes,
Yeah. So they're not, the set is not the same.
yes.
Got it.
It's a very analytic proof. It reminds me of the proof I knew of Weierstrass theorem, for instance. And I like this quotation from Cantor because it gives, I think, the right idea that was presented already today in two other occasions, similar to those which was presented today. It's a translation from the original German, and I'm sorry I cannot read German, so that's where you get it. And it gives an intuition of what a well-defined set for Cantor was. And the way I like to read it is that you need to give two bits of information to get a set. You have to know which are the elements that you want to consider and which is the identity that you want to consider among those elements. And an example of the real numbers as constructed by Cantor is a perfect match for that idea. The Cauchy sequences, and many Cauchy sequences give you the idea of the same real number, and you determine that two Cauchy sequences are the same real number, if you want to say they are equivalent, say it like that, when they converge to the same one. But actually you can say it without referring to the notion which you're trying to define, and you just require that the sequence obtained by the differences, the component-wise differences, goes to zero, which is a rational number, so that limit exists before you define them. With that idea in mind, and I move to the second proof of Cantor's, that Cantor himself produced for the theorem about cardinalities. It's slightly different. It doesn't speak of the real numbers, where we know that the real numbers are in a bijection with 2 to the power n, but in fact, it is exactly using those two sets, the natural numbers and the set of functions from the set of natural numbers into a set which is the letter M and the letter W. And I thought that was so beautiful in the original paper. In fact, the characters used in Cantor's paper exactly what are the reflection of one of the other. So let's assume that there is a surjection, not just a bijection, but just a surjection from the natural numbers into the double tone raised to the power n, and change the point of view completely. Take any end of function of the double tone into itself, any. Yeah, we know there are 4, but take any of those. And consider the function g that I've written up there. It is defined using the surjection. The surjection takes a natural number, enumerates, if you like, the functions from the natural numbers into the set of m and w. So when I take sigma of n, I get a function, and I can apply that function to the number n. Yes, it's complicated, but that's the way it goes. Since there is the assumption of surjectivity, that function g must be the value of some number k in the original n, in n up here. Okay? And so now let's compute f of sigma k of k. F of sigma k of k, just by pattern matching, you see is precisely g applied to k. I've just substituted k in place of n. But sigma k, I'm sorry, g is sigma k. So I substitute g for sigma k and I obtain that. In other words, if I read it using the external parentheses, I don't know if this is going to work. Yes. That number, whatever it is, sorry, that element, m of w, whatever it is a fixed point for f, because f changes it to the same number. So f has a fixed point. But there is a function, one function, out of the 4 functions available from the doubleton into itself, which has no fixed point. And this is the argument. This is exactly Cantor's argument. It's obvious, it was obvious to him already, that it doesn't rely heavily on the natural numbers, and in fact, he extends it immediately to any set. If you have problems in reading the function that on numbers that produces a function on number, let me introduce a notation for, well, for the same function written as just as a function of 2 arguments, call epsilon the function that takes 2 numbers n1 and n2 to the function sigma of n1, which is a function, applied to n2. And I can change, because I prepared the slides, everything accordingly. So the function g gets written like this, which is easier to watch. The condition of surjectivity changes slightly because now, well, I want to refer to epsilon. And so epsilon is a function of 2 variables. I have to compare it. No, I just write down the identity of functions by extensionality, and the fixed point, it's just a matter of, well, of getting rid of a few parentheses. The final thing does not refer to epsilon, does not refer to sigma. It's a property of functions just of the second set involved in the statement. There was a little exchange between Cantor and Frege at the time of the publication of Frege's theory, that where Cantor claimed that it was obvious that the theory had some problems because the argument that we've just seen applies again. I call this the Russell's paradox, I'm sorry, because it's essentially Russell's paradox. I've never seen it written like this. I know the construction. In fact, I have the actual proof coming up in a few slides, but it is just taking, instead of n, this universe assumed as a set, U, and using it to raise the doubleton to the power U. And then the same argument works because the universal set, if it exists, contains all possible sets, and in particular contains the set of functions from U into the doubleton. And so you generate a surjection, and there is a fixed point for every function on the doubleton, and that's no good. That was the idea that was developed in the paper by Lovia that I mentioned at the beginning. And since I'm not going to assume that everybody here is fluent in category theory, I decided to state the crucial theorem by lemma, in fact, by Lovia in 2 forms. One which refers to category theory and another which doesn't refer to category theory. Because after all, well, it is very interesting because it shows that the argument, the diagonal argument of Cantor can apply in any category with very little structure. Just
Excuse
as-
me, before you go on, just, did you say that that proof that you just showed us was actually due to Cantor in his correspondence to
No.
Frege?
No,
Oh,
no,
okay.
no, it's just that Cantor suggested to Frege that it was obvious from his result that there had to be a problem.
I see, I see.
No, 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 no. That was just my copy and paste of the previous slide because it's just the same argument. I don't even know if he mentioned in which paper that the original proof appeared to Frege. And so the structure required is just that of a category with finite products, and one assumes that there is a pair of objects and an arrow which satisfy a certain property. I've used essentially the same letters that I've used in the past two simple proofs. So I'll let you read it, and the conclusion is that a certain endo arrow f from B to B has a fixed point. I can restate that same theory by using any theory with just identities in a typed language. I prefer to use types because, well, I prefer to think of A and B as separate types, not necessarily obtained from the same sort in a first order language with one sort. So the same condition that I've written above using the categorical language can be repeated in type theory, in simple type theory, by saying that one has to assume that it is possible to write a term epsilon of A1, A2 in the given theory with the property that for every given term G with one free variable from the type A and of type B, there is a constant term of type A such that that equality is provable in the theory. If that is so, then every endoterm, I don't know how to say it, every F taking a free variable in B and producing a term in B as a fixed point. I'm sure you can imagine the proof, but I'm going to give it to you anyway, and I give it to you in both forms, unless you raise your hand and say that's enough. Because I think that the categorical proof, there is going to be no words in this, explains the structure of what goes on, or part of the structure of what goes on. So, well, you certainly remember the first two examples of Cantor's original proof. Take any function, take any arrow, f from B to B, and consider that commutative diagram. In other words, define G as that composition, where the only difficult arrow, if you're not fluent in category theory to understand, is this one, which is produced by universal property of the product A times A from the two arrows of the identity of A from A to itself. It's the diagonal. It's the diagonal method. The diagonal has to appear somewhere. There it is. Well, it's going to reappear a few times. Because of the assumption, G is of that form, where from A into the terminal object of the category. And from there, I go with K into A. Okay, so that's the use of the hypothesis. And now I have to compute the fixed point. And the fixed point gets computed by using all the commutativities that I have appeared now. And the fixed point, actually, one sees it by going up that way with that composition, which is the pair of the arrows K and K composed with epsilon, composed with F, and down here, where you find again the pair of the arrows k and k, and the only arrow epsilon. In other words, in the composition along the path below, f has disappeared. That is the fixed point. If you didn't like this proof, here is the other one. And I let you look at it because, I mean, it's just a hat trick. It's the usual hat trick, and the chain of identities is the usual chain of identities. The thing that I find useful, if I can flip back to the previous slide, about the diagrammatic construction is that you see where all the pieces get together. And in particular, you see that there are uses of the diagonal, but also of many other kind of diagonals. Okay, so I'm basically done, which is very good for your plan.
Oh,
Yes,
so
don't worry, I have many slides still.
okay. I should ask something to slow you down. So this means that, for example, the category of sets is not going to satisfy these conditions because otherwise every function would have a fixed point. But we know that there are functions that don't have fixed points. So which kind of categories are these?
Very good question. First, I'm taking the well, let's say both statements. I said nothing about the objects A and B, but if I take B to be a singleton, then it works, even in the category of sets.
Yes. Right. And the antiset also
Yes,
works?
and well, and the empty set may work because I have to choose appropriately if I choose appropriately A. And yes, so the examples are coming up.
Okay.
And some of those are going to be special. Still Plovius theorem. Let me go quickly through the first two examples. In the first case of Cantor's second proof, original proof, I have to take the category of sets. I have to take A to be the natural numbers and B to be the doubleton. Then the proof, the lemma will assure me that if a surjection exists, then every end of function on B has a fixed point, which gives me the contradiction I was looking for. Happier? Same thing for Russell's paradox, absolutely the same, just that the object A, the set A, is different. Russell's original paradox, that was performed in Frege's theory, using essentially properties derived from basic law 5. And well, I've written it not in Frege's language because otherwise I had to have time to explain Frege's language. And from basic law 5, you derive the property that I've written up there. For every property G of X, where X is any set, there is a set which I called K, the set of all X's which satisfy G, if you like, such that the property of X being in K corresponds precisely to the fact that X satisfies G. It's equivalent. But if I use A, as I write there, as the type of set with respect to provable equality in the theory, whatever equality it is there, and B as the set of propositions with respect to the equality of provable equivalence, then I'm within the action of the lemma, and I get that every property of propositions, f of beta, has a fixed point. And again, if I pick a specific, I don't know if there are 4 functions on the set of propositions within Frege's type theory. Probably there are none, or maybe just one. But if I take negation of a property, that cannot have a fixed point, because if I assume a fixed point for negation, I derive a contradiction. And that's it. This is precisely the form of the paradox given by Russell. Another case where you get an example is Church's fixed point operator. The untyped lambda calculus suggested by Church in the 1920s, something around there, is a completely different approach to the foundations of mathematics than that of sets. It uses as a basic notion that of a function, and I mean, I'm really skipping a lot of the details, but just think of the universe where mathematics lives as being composed of functions that act on element of the universe. So they act on functions. So anything we can speak and construct are functions. And in particular, you can apply a function to a function to obtain a function. It's how it works. In fact, one of the things that Church declared was that it was possible for every function on the universe, f, to be encoded by an element of the universe. And in order to understand how the encoding worked, he introduced a binary operation of application, of evaluation of a function x1 on another function x2. And essentially, the only condition that he was requiring was the one I've written here, that evaluating the code of a function on any element returned to you exactly the same thing as the term you started from. And but that is precisely the way we have seen the epsilon term work in the general case. And in fact, it is a theorem of Church's that every term you can construct in the untyped lambda calculus has a fixed point. If that bothers you, well, then let's talk after the two talks today about the untyped lambda calculus. But it is like that. If you think that cannot possibly be an empty set, you're almost right. But after all, everything is a function, not a set. So the empty set doesn't even appear. And in order to see how the structure of the lemma applies to this case, take A to be the type of the universe of functions, and B, the same type where, so you want to prove within the theorem if two functions are equal, using, as I said, the identity of beta reduction. In fact, I've expanded here the definition of the fixed point that gets computed. And again, when you read textbooks on the lambda factor, which is the basic paradigm for functional programming now, so it is fairly relevant, you see several explanations of why the construction of this incredible result of a fixed point, given any construction in the lambda calculus, is so complicated, because it is complicated. And again, I find that the explanation given by the categorical diagram of the first proof of Lovier's lemma explains why epsilon eval in this case appears so many times. Another example. You're probably aware, if you know the solution of Turing to the halting problem, that there is an argument by diagonalization there, essentially by diagonalization. The fact is that the argument is precisely by diagonalization. So the story goes a bit longer than the previous one. Turing, essentially at the same time as Church, decided to discard the untyped lambda calculus because he feared it was inconsistent, came up with the idea of a computing machine, which are now known as Turing machines, and proved a fantastic theorem of the universal machine, which I've written using the language of partial recursive functions because I don't want to get into all the details of encoding Turing machines. So I hope you don't mind if you read the result using partial recursive function. After all, partial recursive functions are precisely those which are computed by Turing machines. And there is a specific Turing machine which evaluates a partial recursive function which I named F, which takes a pair of natural numbers, returns possibly a number. In fact, one knows the property that evaluates all partial recursive functions of a single value, as it is written up there. The identity of the computation is written taking care of the fact that the functions are partial. So what has to happen is not just that two values are equal, but the two functions, partial functions, have to be computed exactly on the same argument. And when the argument is one of the domain of the two functions, then the two values coincide. So it's identity of partial functions, which has to be written in this complicated form. There is a standard notation for that, which is that of a Venturi tube instead of an equality, which means when one side is defined, so is the other, and they are equal. And I hope you let me use that. Again, I have to explain it not in terms, well, I have to explain it in terms of values, and the values are on arguments in the natural numbers. A corollary of that result, as proved by Turing, is that there cannot be a total recursive function that decides the halting problem. And by deciding the halting problem, E means exactly this. Hilbert meant something like that. But I'm not going to go into that unless you ask. So, depending on a choice of a code for a partial recursive function, and given an argument to that partial recursive function, I have to be able to determine if the computation converges, is defined, or is this not defined. And the request is that that can be done.
So should the A be the E or the E be the A?
Yes, the E should be the A. Thank you. And that corollary is proved by the diagonal method by first, well, assuming that there is such a total recursive functions in two arguments, and using it to extend the partial recursive function given by the universal machine theorem to a total recursive function. I mean, I always like to think of that definition as computing sequentially the product of the two functions. And by sequentially computing the product, I do not mean sequential multiplication but of the digits, but I really mean first compute this function. If it is 0, well, there is no reason to compute the second argument because it is 0. And if it is 1, then go ahead and compute the second. And it is a total function because theta ensures that it gives a result in any case. Therefore, the same statement which is written in the universal machine theorem can be restricted, strengthened, modified, say it anything you like, to a statement not about partial recursive functions, but about total recursive functions. Because now the function of evaluation is total. So you're certain that it returns total values all the time. And at this point, we are in a situation where we can speak of functions and taking A and B in the lemma to be the natural numbers and using just partial total recursive functions in using the language, if you like. The terms can be constructed using only recursive functions and identities of recursive functions. We get the contradiction, because among the recursive functions, end of functions from the natural numbers into the natural numbers, there is the successor function, which has no fixed point. There is another version. Now I do care about doing that. There is another version of the universal machine theorem that applies by diagonalization to prove another theorem, which is a positive theorem in this case, which says that the recursive functionals on the partial recursive functions always have fixed points. And in this case, the set, again, terms are constructed using recursive functions. So they're not all functions from the natural numbers or to the natural numbers. They have the condition to be given in a computational form. And the recursive functionals are just the right thing to use there, because they are those functions on the set of partial recursive functions from the natural numbers into the natural numbers can be described on the codes extensionally. And that's exactly the condition that one needs in order to apply the lemma to get a positive application and fixed points for functionals. I think, yes, I have still time for one final remark. Well, from how I always read the proof of Gödel's incompleteness theorem, there was a diagonalization in place somewhere, and I remember discussing a long time ago with a friend physicist that was fascinated by Gödel's argument, that he could understand the self-referentiality of the theorem, and he was trying to find an abstract approach to it. And I was arguing that the main point about self-referentiality was just in the argument, but that the structure beforehand was that of being able to consider certain elements as acting as functions on other elements. And what I find really amazing in the proof of Gödel is the fact that he imagined that once you've encoded using Gödel numbers, all the well-formed formulas of, I use Peano arithmetic up there, but any theory that axiomatically extends Peano arithmetic with the numbers, the crucial point is that of explaining substitution of a variable for a term in a formula. And that's the way the application in that case works. Then the real genial part is that of imagining the correct formula F for which to look for a fixed point that will give the incompleteness. And in fact, it took a few years to get the right one. But I think that was all I wanted to say. The proof method of diagonalization depends on a structure that can be recognized. In fact, I would hope that in the future days, while I'm still here at Chapman, somebody comes up with possible other examples, because I think it is difficult to find examples, but they are there. Thank you.
Your turn. Ben, go.
You said you'd like further examples of what
Please.
exactly? I think I drifted right at the end.
What exactly, what kind of
of
example would you like?
applications of the lemma, of the diagonalization,
I see.
because I think we can see mathematically what the diagonalization method is, and but we need examples. In fact, some of those I've listed come from the original paper, but 3 of those I've listed are nowhere. And not even in the other 2 papers. The other two papers by Janowski and Abramski refer more, if I may continue on that, refer more to the fact that at a certain point in the method, oh, it's here. Yes, you're not really interested in using epsilon in 2 variables, but you're just interested in the behavior of epsilon on the diagonal. Yes, but I mean, I don't see any example of a structure where you don't get to that behavior because you have already a function, an arrow in 2 variables. So that's what I'm looking for.
A lot of people. So Piotr,
Mike,
and Giovanni.
Understand
No,
with I
perfectly.
I will give you no details. In non-standard analysis, when we prove saturation of non-standard reals, we apply.
If you write on this part, people on Zoom can see it.
Okay. I will don't take the details, just consult any book on non-standard analysis and saturation argument. It's but definitely goes as a diagonal. But what is interesting is the history, because Cantor gets credit to originate, to devise this argument. It's not the case. It was Heine in 1872 when he constructs real number, and he provides, he proves that the reals he constructed are Cauchy complete. And the argument goes like that. You get a sequence of real numbers, which means a sequence of rational numbers. Okay? And this sequence is a Cauchy sequence, and it has to have a limit. And it shows that's the limit, that's the Heine. And the counter argument comes from, I guess.
And it's 87, I think. Oh, the first argument, no, it's already 80.
Anyway, I think it.
So what's the statement of Heine? Can you please repeat? I didn't understand what statement is he.
That real numbers are Cauchy complete.
Uh-huh.
So a real numbers is a sequence of rational numbers. And you get a sequence of real numbers, which means a sequence of sequences. And you are looking for a limit of this sequence. And he shows that that's the limit. It's very concise, so people
Very nice.
hardly can, let's say, decode it. Anyway, it is. Anyway.
Yeah. Heine was
So I
the
think it's the
advisor
first
of
one.
Cantor, no? Wasn't
Yes.
Heine the
Are you sure it is
you.
independent of Cantor? Because Cantor gives a similar proof in his paper on the convergence of trigonometric series, where he uses the definition of
Yeah.
Cauchy
And
reals.
Cantor never proved the completeness of real. Never. He takes it as a granted. Never proves.
He takes it.
As a granted, he takes it. He
Oh,
accepts.
so the
Cantor
proof I
never-
saw was not of his.
No,
So sorry.
Cantor never
No,
proved
yeah,
that the
that-
real numbers are Cauchy complete. Cauchy complete. He gave it. I know.
Yeah, but okay, if I may, thank you very much. If I may comment on that, that's the diagonal construction. Then there is the further step of
contradiction?
inducing a fixed point for certain functions. Yeah, I look at that paper of Heine. Thank you.
It's not translated into English.
Bad. There is Google.
Mirna, Giovanni, cos'è?
Okay, so you wanted examples of the use of the diagonal argument. So I thought I could give 2, one you kind of gave. So when you look at the non-standard model of the natural numbers, you take an alpha power.
Yeah.
And now you want to show that this is that there is a number which is less than all the natural well, that is, there is infinitesimal.
Yes,
And in fact, that's a diagonal of
yes.
the numbers that are smaller and smaller. So this is, and the fact that this is non-standard is the
Yes,
analog of
yes,
the conservation.
Yes,
Yeah.
you're right, thank you.
I think that was your idea as well.
Saturation were a bit different. Anyway,
But another argument also is the method of forcing of coin. So when he forces, so maybe I can draw this on the board because it's.
Oh, yes.
Yes, so the very simple forcing that he wants to force a new function from omega to 2. So what does it mean, new function? So he has some universe of set theory, let's call it M, which is countable. It's a countable transitive model of enough of Zn. Of course, not of everything, because it's a countable set. So we call it ZF star. And so since it's countable from the point of view of the outside world, it has countably many functions from omega to 2. Let's call them E0, F0, okay, F0, F1, and so forth. So these are all the functions from omega to 2, which are inside of M. And now we're going to construct a function from omega to 2, which is not there, by doing the following. We look at all the partial order of all functions which are from omega to 2, and the domain is finite. So these are partial functions. And we're going to extend them just by extension. So F is, I like this is Cohen's notation, F is weaker than G if G is superset. Okay, so we are extending, building beta functions, and we show that we can, for every one of those Fn's, we can find a dense set Dn is all the F such that there exists something in the domain of F such that F is different on this K than the function Fn. So you are diagonalizing against them. Yes, and then the fact that you can find the generic filter would intersect all of these, you take the union and that's your new function. So,
Thank you. Yes.
Giovanni, I think in the order, Giovanni.
So you asked for an example and I answer not very correctly with a question.
No, but I asked.
So not a conjecture, but a hint towards what could become an example. First, I must say that when you were talking in the first slides, I realized I have been saying some awful things several times, namely that usually fixed points are the result of a limit. While what you showed is that fixed points,
Not me.
you
Okay,
recalled.
Yes.
What you recalled is that there is quite another construction. So when I say fixed point, when I wrongly say fixed points are the results of a limit, it's to insist that to the opposite of this, the fixed point of probability logic are not obtained by a limit.
Yeah.
So the question is, are they an example of this? I have a further little step.
Thank you for asking the question.
Usually there is the wrong understanding that the fixed point theorem proves
Which fixed point theorem?
the Young-Sabine fixed point
that,
theorem.
yes.
Sorry.
Yeah, that one. No, but-
Self-reference. The fixed point theorem is considered a proof that fixed point exists. This is a wrong statement.
Because it's constructed.
No, it is constructed.
Yes.
My proof is totally constructed.
Yes.
You can instruct a computer to find a fixed point, contrary to, and it is also intuitionistic. That's not the problem.
The fixed point exists, but
Yes, it's not that fixed point exists. the proof shows that if you assume one fixed point, then you obtain all other. Because the Loeb's formula, formalized Loeb theorem, says precisely that there exists one fixed point of the formula box of something implies, I don't remember precisely. So you can read the characteristic axiom of probability logic, Loeb formula, as an example of fixed point. And then the proof, the theorem says, if you have that fixed point, then you can derive all other.
Thank you.
Giuseppe.
So I suppose that you didn't try to list all the examples of this.
No.
Of course, one famous one is the the truth of the arithmetic, right?
Yes.
Yes. Okay. So my question then to you is, what about the famous fixed point in topology? Is this one example of this kind of?
That's another big question.
Browse fixed point.
Yes.
And I'm afraid I have an answer there. Well, the direct answer is somebody has tried, not just me, and failed. Me too. And we doubt it is an example, but it's difficult to say.
And another very famous fixed point result is the one that says that if you have a monotonous map, endomap, then this
Like you were saying.
yeah. So is that also an example of this?
No, in fact, there is a thesis by Felipe Garo where he proves that the result I stated about partial recursive functionals, produces a fixed point, depends on, of course, you would say, it depends on the Gödel encoding of the encoding of the Turing machines, and if you vary that appropriately, you get the same fixed point in applying your construction to the case of partial recursive functions. But it is one instance of the very many possible. So essentially the argument is that the two things can be reconciled, but with further assumptions around. And that's the only answer I know. Thank you.
Two points. The first one, Gödel is an example.
Yes.
Is there?
But not, I mean, Gödel used the diagram. The proof of the incompleteness relies really. I mean, the diagonalization was a simple trick, I guess, for Gödel. The real nasty thing was to find the correct F.
Yes.
Yes. Yes.
The correct what?
F, the function, the formula F, where you go to some, which you use to determine a fixed point, because essentially implicitly there you're not discrete. It's not like M and W where you see that they are different, and you have provable equivalence, which is something you're talking about.
Okay. I have another point. I want to write something elementary because the point is very elementary, but Mirna, can I eliminate?
Of course, it's
I eliminate it.
Eliminate a provision.
so polite. Yes, please.
In the Cantor theorem, what you ask is whether there is a bijection between a set
Yes.
and its power set. No? And so you suppose that this bijection, there is a call, for example,
Yeah.
call it phi, and insofar there is a dejection is subjective, and so it means that there is a double V here, such that here we have something like that, correct?
Yes.
Okay. Now, this is the set of the subset of that. So this is a
Yes.
element, a subset of that. And so now, when you want to develop the proof, you arrive to construct something as a set, let's say X star, that is such that an element W is an element of
Yes.
X, if and only if W is an element of X and W is not an element of phi of V, correct? This is
Yes.
what you do. Okay, now my point is this is clearly the statement of Russell paradox, but it is clear. You said there is something more, much more relevant, it seems to me here, because here you are supposing that it is by definition a subset of X. And then you have not only the paradox, also the solution. You have separation here. You have separation here.
Yeah.
So how is possible that nobody saw it before that one?
Well,
There is not a paradox. There is also the solution of the paradox. Written here, it's written.
Well, if
I-
you actually like that.
Because the paradox does not bring to a contradiction, bring to a theorem. And why it does not bring to a contradiction? Because we are supposing that it is a subset of a given set.
well,
So this is the question that I want. Why is it possible that nobody solves the solution that is
you may argue, and this is really difficult. I'm putting words in the mouths of people I spoke to and asked. You may argue that Cantor maybe saw this argument when he wrote to Frege, explaining to him that his argument. Mind you,
Cantor, Russell.
Cantor.
They mentioned
When you go, okay.
No, independent of, I really don't know whether he knew about Russell writing to Frege. And yes, I agree with you, but as I said, I never read that. I just know about it. I never read the actual, and it was all in German, so I couldn't. I mean, I can ask him. And it's possible that he suggested something like that. Certainly, that appears a few years later in ZF, in Zermelo's work of
But the problem that appeared in the Melo work in 1908, there is not a version in 6, no, published in 8, but in any case, 8. So it means 25 years after. And after the proof of Cantor.
But
Wait, more. The proof of Cantor is
No, but-
the proof of Cantor is
80, if I remember correctly, 87 and 92.
But not this simple
92.
one.
In this way, is using 92. I have here. So it's 7 is mean 15 years before. How is possible that they took 15 years to see something that is already written in the proof of Cantor? That is the solution, is separation. This is the question. In the proof of Cantor is written the paradox, but the paradox is not used to derive a contradiction. It's used to prove a theorem. And why the theorem is proven there is no contradiction? Because we suppose that the set is a subset. So is already the
I
solution.
would say Cantor's proof is really in the form I listed it here.
Yes, the proof of Cantor is a little bit more.
Yes.
I agree.
Yes. So, and another thing, for my understanding of reading Cantor, is that he really didn't care very much about constructing subsets. He was more concerned about constructed sets out of sets.
So you mean that we see it now because we have
we have
in thermal
yes,
approach?
yes.
Possibly.
And again, I mean, after all, Zermelo wrote his axiomatic study in Cantor. So
But
I
okay, I have another question. But go if this.
I am sorry for another self-reference, but exactly the same.
that's
Yes, the talk of
That's the topic.
exactly the same surprise that Marco expressed. How come they did not see? I asked myself when I discovered not long ago that the approach of distinguishing sets from collections and distinguishing sets from subsets is clearly consistent. You don't need the program by Hilbert, proofs. It's clearly consistent because try to express, I don't have a rigorous proof, but try to do any of those and it will not succeed because anything is typed. You cannot give untyped definitions like.
But
So
I possibly say something completely wrong, but let me making everyone understand.
yes,
Your distinction between set and subset does not reflect on a lower level the distinction between set and classes?
no.
No?
No.
In no way?
No, the distinction between set and class is realized by Cantor himself. So it's not in the spirit of set collection. It's more in the spirit, it's too big.
Okay.
While the spirit set collection is you generate.
I just wanted to make a comment that maybe answers your question. There was a conference maybe a year ago in Barcelona, which was titled, "What can philosophy do for set theory?" And people had lots of answers.
Nothing.
No, but I think it's just the opposite. What you just proved is what philosophy can do for set theory. Because if the first step is to ask the right question, the first step of seeing what you have just written here is asking the right question. Cantor didn't ask this question. I think that's what the same thing as well. And that is it. He didn't have the philosophy. He had a different philosophy. He was looking for something else. And it happens often.
I agree, yes.
Anyway,
Yes.
I have another point related, but about Frege. Cantor wrote to Frege, he showed the problem, and Frege apparently did not understand. There are two explanations, possibly both of them good, I don't know, just not exclusive. The first one is simply did not understand Cantor theorem.
Frege didn't read German.
Frege, no, did not Frege was not reading a lot of secondary literature. So perhaps he did not know the original paper by Cantor and why Cantor sent the letter. The letter was not so explicit. So it's perfectly possible that Frege did not see the mathematics behind. Okay, but this is an explanation. But there is also another, that the argument requires strongly an extensional notion of a function. And Frege did not have such a notion. For Frege, a function was an explicit law, an explicit algorithm.
Without quotienting over extensionality.
An axiom, a function was a formula that I can write in a language. And so if you have this notion of a function, there is no contradiction here. You can perfectly have a bijection between a set and its power set. So I think that one of the reasons is simply that Cantor and Frege did not share the same conception of a function. And for us now today, the extensional notion of a function is trivial because we know what another conception brings to that we have limited our capacity of making mathematics. But Frege was really as completely another point of view. So for him, there is not a contradiction here.
But I don't understand your argument, because what this argument is proving is that there is no function, whether it is definable by a formula or not definable by a formula. So
But
why
you,
would they?
but you have, sorry to interrupt, but you have to use them. in the argument. And there's,
But the argument could be then, okay,
Yeah, but
suppose
the
that you
phi-
have that phi is given by a formula, then blah, blah,
Yes,
blah, blah,
yeah.
blah, blah. So everything follows.
No, but,
no,
but
but-
you,
but
but you
you-
have to understand
there is no
PX
such-
as well in the same way.
But it's
How
not
is
the
it-
function that the fact that
Also-
the function is given by a formula, but the fact that the subsets are given by formulas too.
my
The
understanding,
subsets are given by formula.
So that's the point.
That's the
Not-
point, yes.
Not,
Yeah, yeah.
not the function.
No, the subset.
Yeah.
The subset are given
Yeah.
by a formula. That's what,
that was.
any,
would have been my
of course,
answer.
any subset.
Sorry.
No, of course. This is any function. Okay, so of course.
Yes. In fact, if I may add just one little comment, it is, I mean, my understanding is that reading lots of this text, it was quite clear that a crucial notion for them was that of function rather than set. They had to eat sets because they wanted to understand functions. Whether we understood.
By the way, for Frege, there are no set. Set are simply extension of functions. So the real basic notion is function of set. And when Russell wrote the letter to Frege, he wrote the letter set, but Frege immediately translated it in terms of functions. And when in the way out, the appendix of the second volume, the set, they try to go out. It does not formulate the paradox in terms of set. Formulate the paradox in terms of function.
And the other comment that goes with it is that Church never published anything on the untyped lambda calculus because he feared it was inconsistent.
Mm-hmm.
And it took 50 years to find the model.
Mm-hmm.
May I also
Yes.
comment? You had this very nice remark about the other thing completeness theorem, and that the hardest thing was to find this function which will have the fixed point. In fact, that also shows how important to Gödel it was to have a concrete function, because just if he wanted to stop at saying there exists such a function, it's a two-line proof.
You're right.
Yes, but it's not only for this reason, also because Gödel needed to have a theorem that was not in formal set system. Because if he had to write the function, the proof of theorem of Gödel cannot be in a formal system, because otherwise, then you have the problem about the consistency of the formal system which you are. So he wanted a proof that was absolutely constructive,
Constructive.
not because he was Giovanni, not because he liked constructivism absolutely, but it was the condition of the
Of
proof.
the proof.
Otherwise,
Because he was the first to understand fully the difference between language and meta-language.
exactly. So
And
he needed to
Could not prove.
construct.
Gödel,
Yes,
Yeah.
you are totally right.
After
It's more than
Brouwer.
just a theory.
the first one who proved a theorem using that
Okay.
difference.
Other questions, remarks, objections, protestations? I always say to the students, they should protest, but they never protest. Okay,
Because they're- Thank you.
thank you.